camera glides slowly over Greenland's eastern coast, where towers of ancient ice rise hundreds of feet above dark water. Meltwater streams trace brilliant blue veins down white cliffs, and in the distance, the gentle groaning of glaciers fills the Arctic silence, a sound like the earth breathing in its sleep. The air is crisp and still, carrying the faint mineral scent of rock dust ground fine by millennia of ice movement. This is a landscape that appears frozen in time, unchanging, as permanent as stone. But beneath this frozen surface, far below the ice and the bedrock it rests upon, something warm and patient has been discovered. A hidden geography of heat that scientists have only just begun to map in detail. For years, researchers have understood that Greenland's ice sheet doesn't simply sit motionless atop the land. It flows, imperceptibly slow from a human perspective, but constantly in motion, sliding downhill grain by grain, molecule by molecule, responding to gravity and the subtle influences of temperature and pressure. What shapes this movement? What determines whether glaciers creep forward or surge toward the sea depends on far more than just the air temperature above or the ocean currents lapping at ice margins. Deep below in the mantle, that thick layer of hot, slowly churning rock that lies between Earth's thin crust and its molten core, variations in temperature create invisible patterns of heat that rise upward through miles of stone, eventually reaching the base of the ice sheet itself. In some places, this geothermal warmth melts ice from below, creating thin films of water that act as lubricant, allowing glaciers to slide more easily toward the ocean. In other places, where the mantle runs cooler, ice stays frozen firmly to bedrock, held in place by friction and cold. Until recently, scientists working to predict how quickly Greenland might lose its ice, and how much it might contribute to rising seas, had to work with rough, blurry estimates of this hidden heat. They knew it mattered. They knew that if you got the basal temperature wrong, your models of ice flow would be wrong too. But the tools to see clearly into the Earth's interior, to map temperature variations with precision across an entire region as vast as Greenland, simply didn't exist. Models of ice sheet behaviour had to make do with simplified assumptions, averages, guesses informed by limited data. It was like trying to predict how water would flow down a hill without knowing where the hill was steep or gentle, rough or smooth. Now, in the quiet laboratories where geophysicists spend their days coaxing meaning from seismic waves and satellite measurements, something has shifted. A team of researchers led by scientists at the University of Ottawa, working in collaboration with colleagues in the Netherlands and Denmark, has produced the most detailed three-dimensional temperature maps ever created of the upper mantle beneath Greenland and northeastern Canada. These maps don't show the surface, they show what lies miles below it, revealing a landscape of thermal variations, ribbons of warmer rock, patches of cooler material, all arranged in patterns that reflect the deep geological history of the North Atlantic region. The work involved combining multiple types of geophysical data, measurements of how Earth's gravity varies slightly from place to place, recordings of seismic waves from distant earthquakes as they passed beneath Greenland, and sophisticated computer models of how rocks behave under extreme heat and pressure. The computational effort alone was immense, with supercomputers running hundreds of thousands of simulations, testing different possible temperature structures until the pieces fit together into a consistent picture. What emerged from all this patient calculation was a portrait of Greenland's thermal underworld far more complex than anyone had previously documented. The mantle beneath this massive island is not uniformly warm or uniformly cool. It varies significantly from region to region, shaped by the island's long journey through geological time. The models reveal that beneath certain parts of Greenland and northeastern Canada, the mantle retains traces of ancient heat, signatures left by the Iceland hotspot, a deep, long-lived source of volcanic heat that has influenced the North Atlantic for tens of millions of years. As tectonic plates shifted and Greenland drifted slowly across Earth's surface, it passed over this hotspot track, much like a piece of paper moving over a candle flame. The heat left its mark not just in the volcanic rocks that still dot the landscape above, but in the thermal structure of the mantle itself, patterns that persist even now, warming the base of the ice sheet in specific locations. To understand how scientists can see temperatures miles beneath the surface without drilling a single hole into the Earth's interior requires understanding how seismic waves behave. When earthquakes occur anywhere on the planet, they generate waves that radiate outward in all directions, passing through the entire body of the Earth like ripples spreading across a pond. These waves travel at different speeds depending on what they pass through. In cooler, stiffer rock, seismic waves move faster. In hotter, softer material, they slow down. By recording these waves at seismic stations scattered across Greenland and analysing how their speeds vary, scientists can infer the temperature structure of the rocks the waves pass through. It's an indirect measurement, a form of planetary X-ray that requires sophisticated interpretation, but when combined with other data sources, gravity measurements that reveal how density varies below the surface, knowledge of rock physics and how minerals respond to temperature changes, it becomes possible to build detailed thermal models of the deep Earth. The new temperature maps show warm mantle material beneath portions of Greenland and northeastern Canada arranged in patterns that align with the known track of the Iceland hotspot. Tens of millions of years ago, as the Atlantic Ocean opened and Greenland separated from Europe, volcanic activity associated with the Iceland plume created massive lava plateaus in what is now Greenland's eastern coastal region. The rocks cooled, the visible volcanism ceased, but the deeper thermal signature remained, a ghost of ancient fire still radiating heat upward through the crust. This warmth doesn't create dramatic volcanic eruptions today, but it does raise the temperature at the base of the ice sheet in certain areas, sometimes by just a few degrees, enough to matter when you're trying to understand whether ice at the bed is frozen solid or wet and slippery. The path from deep mantle temperature to ice sheet behaviour involves several steps, each operating at its own timescale. Warm mantle rock beneath the crust conducts heat upward, though slowly, as rock is not a particularly good conductor. Over time, this heat raises crustal temperatures, and eventually that warmth reaches the boundary between bedrock and ice, the basal interface where the ice sheet rests on solid ground. At this interface, temperature becomes critically important. Ice at the bed of a glacier can exist in different states. If it's cold enough, it stays frozen to the rock beneath, gripping tightly through friction. But if temperatures rise to the melting point of ice under pressure, liquid water forms, a thin film, perhaps just micrometers thick in places, but enough to dramatically reduce friction. Glaciers flowing over this water-lubricated surface can move much faster than those frozen to bedrock, accelerating their journey toward the ocean, and ultimately contributing more quickly to sea level rise. The amount of geothermal heat varies across Greenland's bed, not uniformly, but in a patchy, complex pattern that reflects the underlying mantle temperature structure. In regions where the mantle runs warmer, heat flux through the crust increases, raising basal temperatures and promoting more extensive melting at the ice bed interface. In these zones, outlet glaciers, the fast-flowing rivers of ice that drain the interior ice sheet toward the coast, can slide more readily, responding more sensitively to changes in surface conditions. When summer melt increases at the surface, or when warm ocean water reaches glacier fronts, these thermally sensitive regions may speed up more dramatically than areas where the bed remains colder and ice stays locked to rock. The new mantle temperature maps allow scientists to identify these regions with greater precision than ever before, pinpointing where geothermal influence is strongest and where ice sheet models need to account for enhanced basal sliding. Beyond the direct effect on ice flow, the thermal structure of the mantle also influences how the solid Earth responds to changing ice loads. As ice, sheets grow or shrink. The land beneath them subsides or rebounds, adjusting to the changing weight pressing down from above. This process, known as glacial isostatic adjustment, depends partly on the temperature and viscosity of the mantle rock below the crust. Warmer mantle material flows more easily, allowing faster rebound rates. Cooler, stiffer mantle responds more slowly. Understanding these variations matters for interpreting GPS measurements of land uplift in Greenland, for separating ice mass changes from bedrock motion, and for refining estimates of how much ice Greenland is actually losing year by year. The new three-dimensional temperature models provide crucial input for models of glacial isostatic adjustment, helping researchers disentangle the complex interplay between ice, ocean, and solid Earth. All of this feeds into the larger question that drives so much of the research on Greenland. How quickly might this ice sheet melt, and how much will global sea level rise as a result? The Greenland ice sheet contains enough frozen water to raise global sea levels by more than 7 meters if it melted completely. a scenario that would transform coastlines worldwide, submerging cities, displacing hundreds of millions of people, redrawing the map of human civilization. No scientist expects this to happen quickly. Ice sheets respond to climate forcing over centuries and millennia, not years or decades. But even small fractions of Greenland's ice lost over the next century or two could add significant amounts to sea level rise, compounding the effects of thermal expansion of seawater and melting from other glaciers and ice sheets around the world. Current projections for sea level rise by the year 2100 span a wide range, reflecting uncertainties in future greenhouse gas emissions, climate sensitivity, and the behaviour of ice sheets. Narrowing these uncertainties has enormous practical importance for coastal planning, infrastructure investment, and climate adaptation strategies. Ice sheet models, the computational tools scientists use to project Greenland's future, require detailed input about conditions at the base of the ice. If these models use simplified or inaccurate estimates of geothermal heat flux, they may overestimate or underestimate how fast ice can flow in particular regions, leading to systematic errors in sea level projections. Earlier generation models often used coarse continent-scale averages for basal heat, or interpolated from sparse measurements that couldn't capture the fine-scale variations revealed by the new mantle temperature maps. Some models used heat flux estimates derived from regions with different geological histories, inadvertently introducing biases. The result was a persistent source of uncertainty in projections, a fuzziness in the predictions that made it harder to offer concrete guidance to policymakers and communities planning for future sea levels. With the new three-dimensional thermal models of Greenland's mantle, ice sheet modelers can now incorporate more realistic, spatially varying patterns of geothermal heat flux into their simulations. This doesn't overturn previous projections entirely, or suddenly make Greenland dramatically more or less stable than scientists thought. Rather, it refines the picture, sharpening the focus, helping to identify which regions of the ice sheet are most sensitive to basal conditions, and which outlet glaciers might respond most quickly to warming. It allows models to better capture the real heterogeneity of Greenland's bed, moving from a blurry approximation towards something closer to ground truth. Over time, as these improved models are run through multiple simulations exploring different climate scenarios, the range of possible futures should narrow and the confidence in projections should increase. It's unglamorous work, the slow accumulation of better data and better models, but it's essential for turning speculation into reliable forecasting. The integration of deep Earth structure into ice sheet modelling reflects a broader shift in Earth system science toward recognising the interconnectedness of processes operating at vastly different timescales. Climate scientists study atmospheric changes unfolding over years and decades. Glaciologists track ice flow and melt on seasonal to centennial timescales. Geophysicists examine mantle dynamics and tectonic processes that evolve over millions of years. For a long time, these communities worked somewhat separately, each focused on their own slice of the Earth system. But as the tools and data have improved, it has become increasingly clear that these processes don't operate in isolation. The solid Earth influences climate and ice sheets. Ice sheets and oceans load and reshape the solid Earth. Atmospheric changes force glaciers. Glacier meltwater feeds back into ocean circulation. Understanding the full system requires bringing these perspectives together, building models that span from the deep mantle to the atmosphere, from ancient geological history to near-future climate projections. Recent advances in technology have made this integration more feasible. Machine learning techniques are being applied to map subglacial topography, the hidden landscape of valleys, ridges and basins beneath the ice, using sparse radar measurements and physical constraints to fill in gaps and create high-resolution bed maps. Satellite observations now provide near-continuous monitoring of ice sheet surface elevation, velocity and extent, generating datasets that would have been unimaginable just a few decades ago. Supercomputers allow researchers to run ensemble simulations, testing thousands of different scenarios to explore how uncertainties in one part of the system propagate through to final outcomes. Climate models are becoming more sophisticated at downscaling global projections to regional scales, capturing how temperature and precipitation patterns might change across Greenland specifically, rather than treating the entire Arctic as a uniform zone. All of these pieces, mantle temperature models, bed topography, surface climate forcing, ice dynamics, ocean heat transport, are gradually being woven together into comprehensive ice sheet models that can capture more of the real complexity. There's a strange comfort in the disparity of timescales involved in this story. Human lives unfold over decades, civilizations rise and fall over centuries, ice sheets grow and retreat over millennia, mantle temperature patterns reflect processes operating over tens of millions of years. On a day-to-day basis, Greenland's ice sheet appears unchanging, a permanent feature of the planet's geography. But zoom out to the perspective of decades, and you can see thinning along the margins, acceleration of outlet glaciers, lakes forming on the surface in summer and draining through cracks toward the bed. Zoom out further to centuries and millennia, and the ice sheet becomes a dynamic player in Earth's climate system, waxing and waning in response to orbital cycles, atmospheric composition, ocean circulation patterns. Zoom out to millions of years, and Greenland's journey over the Iceland hotspot becomes visible. Volcanic plateaus erupting and cooling, the thermal structure of the mantle gradually adjusting as heat diffuses and plates shift. The new mantle temperature maps capture a moment in this vast span of geological time. They show the current thermal state of the Earth beneath Greenland, a snapshot of deep heat patterns that have been shaped by millions of years of tectonic motion and volcanic activity. But this thermal structure is not static. It evolves, albeit slowly, as the mantle continues to convect and heat diffuses through rock. Over human timescales, these changes are negligible. The deep thermal structure will remain essentially constant for thousands of years to come. But over the longer timescales relevant to ice sheet evolution, these patterns provide a stable boundary condition, a slow-changing baseline against which the ice sheet adjusts. The mantle doesn't care about decades of human greenhouse gas emissions or century-scale policy decisions. It continues its patient work of conducting heat, convecting material, responding to loads, operating on its own deep timeline. There's something oddly reassuring in that indifference, a reminder that while human actions matter enormously for the near-term climate and ice sheet response, the Earth's deeper processes will continue regardless, following their own ancient rhythms. The immediate implications of this research are primarily for the scientific community. Glaciologists and climate modelers who can now improve their simulations, geophysicists who have better constraints on mantle structure, geologists who can refine their understanding of North Atlantic geological history. But the downstream effects reach much further. More accurate ice sheet models lead to more reliable sea level projections, which inform coastal planning, infrastructure design, insurance risk assessments, and international climate negotiations. Cities like Miami, Jakarta, Venice, and Mumbai, all vulnerable to rising seas, depend on these projections to make trillion-dollar decisions about seawalls, managed retreat, or adaptation strategies. Small island nations facing potential inundation need to know whether they have decades or centuries to plan relocations. Farmers in river deltas need to understand how saltwater intrusion might affect their fields. The global economy, still heavily concentrated along coastlines, has immense stake in getting these projections right. The path from mantle temperature maps to actionable policy is long and involves many steps, many translations between scientific disciplines and between science and society. The researchers who built the thermal models likely spend most of their time thinking about seismic wave speeds, viscosity parameters, and computational methods. The ice sheet modelers who use these models as input focus on stress balance equations, calving parameterizations, and meltwater routing. The climate scientists who provide forcing scenarios worry about greenhouse gas concentrations, radiative transfer, and feedback loops. The policy analysts and planners who ultimately use sea level projections must translate probabilistic forecasts into concrete decisions about resource allocation and risk management. Each step involves communication across disciplinary boundaries, building trust, establishing credibility, and dealing with irreducible uncertainties. The new mantle temperature maps represent one piece in this long chain, an improvement in the foundational understanding of Greenland's thermal structure that will slowly percolate through the system, eventually contributing to slightly better, slightly more reliable guidance for human societies adapting to a changing planet. Looking at the images that accompany the research, false colour cross-sections of temperature beneath Greenland, ribbons of orange and red indicating warmer mantle, blues and purples showing cooler zones, it's striking how much structure exists in what might naively seem like a uniform interior. The Earth beneath our feet is not homogeneous. It's layered, varied, full of history written in temperature gradients and compositional variations. Each colour band represents rock that has been heated, squeezed, moved, and cooled over unfathomable spans of time, accumulating a thermal memory of every major geological event that affected this region. The warmth beneath East Greenland remembers the rifting that split continents and opened the Atlantic Ocean 60 million years ago. It remembers the Iceland plume rising from deep in the mantle, punching through overlying rock to erupt as flood basalts. It remembers the slow drift of the Greenland plate across this hotspot track, the gradual cooling as distance increased, the current configuration where Greenland sits northeast of Iceland, still feeling the thermal influence but no longer directly above the hottest part of the plume. This geological memory, preserved in mantle temperatures, now becomes part of humanity's memory, encoded in databases and computational models that will inform decisions about our collective future. There's a kind of poetry in that transfer. Ancient heat patterns detected by seismometers and satellites, translated into numbers and equations, fed into supercomputers that simulate ice flow, eventually emerging as projections of sea level rise that appear in climate reports and policy briefings. The deep Earth speaks in seismic waves and gravity anomalies. Scientists listen with instruments and mathematics. Societies respond with adaptation plans and carbon emission targets. It's a slow, iterative conversation between deep time and human time, between geological processes that operate at one pace and societal processes that operate at another. As night settles over Greenland's ice sheet, the surface cools rapidly under clear Arctic skies, but the heat from below continues its steady upward march, molecules of rock passing kinetic energy to their neighbours, a diffusion process that never stops, never sleeps. Somewhere beneath the ice, at the interface between rock and frozen water, this geothermal warmth is melting ice molecules one by one, maintaining thin films of water that allow glaciers to slide, contributing incrementally to the slow discharge of ice toward the sea. The process is too slow to see, too gradual to measure in any single moment, but integrated over years and decades and centuries it matters. The ice sheet is not a static monument. It's a dynamic system in slow motion, constantly adjusting, constantly flowing, constantly exchanging mass with the ocean and atmosphere. The deep heat helps determine the pace of that adjustment, influences where the system is most sensitive to change, shapes the response to warming air and warming seas. The researchers who created the new mantle temperature maps have given their colleagues a tool, a more detailed map of one piece of the vast puzzle that is Earth's climate system. Other researchers will use this tool to build better models, run more refined simulations, publish updated projections. Those projections will be synthesized in assessment reports, discussed at conferences, debated in scientific journals, and eventually distilled into guidance for policymakers. The process will take years, the improvements will be incremental, and no single study will revolutionize understanding. But cumulatively, through the patient accumulation of better observations, better models, and better integration across disciplines, the picture of Greenland's future becomes clearer. The uncertainties narrow, the confidence increases, the projections become more reliable. It's not fast, it's not dramatic, but it's how science works, brick by careful brick, building a structure of knowledge that can support the weight of important decisions. Far beneath the ice, in darkness and heat that no human will ever directly experience, the mantle continues its slow convection, warm material rising, cool material sinking, heat conducting upward through miles of rock. The Iceland hotspot continues its deep burn, fed by processes extending perhaps all the way to the boundary between mantle and core, thousands of miles below the surface. Greenland continues its slow drift across the planet's face, a few centimetres per year, a motion imperceptible in human experience but meaningful over geological time. The ice sheet continues its own slow motion, responding to the competition between snowfall that adds mass and melting that removes it, to air temperatures that rise and fall with seasons and longer climate cycles, to ocean waters that lap at glacier fronts, to the hidden heat rising from below. All of these processes interweave, operating at their own timescales, coupled through physical laws that don't care about human priorities or concerns, but that can be understood, measured, modelled, and eventually predicted with increasing accuracy. The documentary closes as dawn begins to touch Greenland's eastern rim, golden light sliding across ice that has turned pale pink and orange in the low-angle sun. Icebergs drift in absolutely still water, their surfaces mirroring the sky, their underwater bulk hidden in dark water, carved from glaciers that have been flowing for thousands of years. Somewhere in the distance, a glacier calves, a thunderous crack and splash, blocks of ancient ice tumbling into the sea, raising waves that will ripple outward for miles. It's a small event in the life of an ice sheet, one of thousands that occur every day around Greenland's margins, but each represents a tiny contribution to the global ocean, a few molecules of fresh water joining the vast salt reservoir, an infinitesimal addition to sea level that, multiplied by countless similar events and integrated over years, becomes measurable, meaningful, consequential. The hidden heat beneath the ice doesn't cause the carving directly, but it influences the system that leads to it, warming the base of the ice stream that feeds this glacier, promoting sliding that brings ice to the coast more quickly, contributing to the delicate balance between accumulation and loss that determines whether the ice sheet grows or shrinks. Understanding that influence, mapping that hidden heat, integrating it into models. This is the work that allows scientists to project forward, to estimate how much this glacier, this sector, this entire ice sheet might contribute to sea level in the decades and centuries ahead. It's work done in laboratories far from the ice, with tools that sense vibrations and gravity, with computers that solve equations, with databases that store measurements and simulations. But it's work that connects directly to the physical reality of ice and ocean and rising seas, to questions about how human civilization will adapt to a changing climate, to decisions being made now that will affect coastal communities for generations to come. The Earth's mantle, ancient and patient, glows with heat accumulated over billions of years, heat left over from the planet's formation, and heat generated continuously by radioactive decay in minerals throughout the interior. This warmth rises slowly, powering plate tectonics, volcanism, mountain building, all the dynamic processes that shape our planet's surface. Beneath Greenland it warms rock, which warms the base of ice, which changes how glaciers flow, which influences sea level, which affects coastlines where billions of people live. The chain of causation is long but unbroken, connecting the deepest Earth to the shallowest concerns of human societies. The new thermal maps are one more link in humanity's effort to understand this chain, to predict its consequences, to prepare for what comes next. The work continues, the models improve, the projections refine, and slowly, patiently, like the ice itself, our understanding deepens. The satellite that captured the first measurements feeding into these thermal maps orbits far above Greenland, passing over the ice sheet multiple times each day, its instruments so sensitive they can detect variations in Earth's gravitational field smaller than 1 part in a billion. These tiny anomalies, places where gravity pulls slightly stronger or weaker than average, reflect differences in density deep below, places where rock is slightly denser or slightly less dense, slightly cooler or slightly warmer. The satellite doesn't see temperature directly, it sees the subtle consequences of temperature, the way heat affects rock density, the way density affects gravitational pull, the way gravity affects the satellite's orbit. From these minuscule orbital perturbations, scientists work backward through layers of physics and mathematics to infer the structure of the Earth miles below. This process of inference, of extracting signal from noise, of building pictures of invisible things from indirect measurements, represents one of the great triumphs of modern geophysics. A century ago, the Earth's interior was largely unknown territory, accessible only through speculation and the occasional volcanic eruption that brought deep material to the surface. Scientists knew the planet had layers. They could tell from its average density that something heavy must lie at the centre, and seismic waves from earthquakes revealed distinct boundaries between crust, mantle, and core. But the details, the variations within those layers, the temperature structures and compositional patterns remained hidden. Today, through the accumulated efforts of thousands of researchers, through decades of patient data collection and theoretical development, through the computational power that allows complex inversions and simulations, the Earth's interior has gradually come into focus. Not with the clarity of visible light, not with the directness of drilling or digging, but with the resolution and confidence that comes from combining multiple lines of evidence, from testing models against observations, from demanding consistency across different types of measurements. The thermal models of Greenland's mantle represent this kind of multifaceted inference. Seismic data provides constraints on wave speeds, which relate to temperature through known relationships between heat and rock stiffness. Gravity data constrains density distributions, which also relate to temperature through thermal expansion. Geological observations, the presence of ancient volcanic rocks, the structure of the crust, the history of tectonic motion, provide boundary conditions and consistency checks. Heat flow measurements at the surface, sparse though they are in Greenland, offer direct but limited sampling of the thermal state at shallow depths. Rock physics laboratories provide the fundamental relationships between temperature, pressure, mineral composition, and physical properties. All of these pieces feed into computational models that test countless possible temperature structures, searching for configurations that satisfy all the constraints simultaneously, that match seismic observations and gravity data, and geological history and physical laws all at once. The resulting models aren't perfect. No model of such a complex system can be, but they represent the best current synthesis of available evidence, and they're vastly more detailed and reliable than anything that existed even a decade ago. The improvement in resolution matters enormously for ice sheet modelling, because the behaviour of glaciers is remarkably sensitive to basal conditions, and those conditions can vary over surprisingly short distances. A glacier flowing across a landscape where geothermal heat flux varies by even 20 or 30 milliwatts per square metre from one region to another might exhibit completely different dynamics in different sectors. In warmer zones, the base melts more readily, producing water that lubricates sliding and allows rapid motion. In cooler zones nearby, ice might remain frozen to bedrock, slowing or stopping flow entirely. These differences create patterns of fast and slow ice, channeling flow into specific outlet glaciers while leaving other regions relatively stagnant. Earlier models, working with coarse heat flux estimates that averaged over hundreds of kilometres, couldn't capture this heterogeneity, and therefore couldn't accurately predict which glaciers would respond most strongly to surface warming or ocean changes. The new high-resolution thermal maps, with variations resolved at scales of tens of kilometres, allow modellers to incorporate realistic spatial patterns of basal heat, leading to more realistic simulations of ice flow patterns. This matters not just for predicting total ice loss and sea level contribution, but for understanding the mechanisms of change and identifying the most vulnerable regions. Greenland's outlet glaciers don't all behave the same way. Some respond primarily to surface melt. Warm summers produce meltwater that drains through crevasses and moulins to the bed, temporarily increasing basal water pressure and speeding up flow. Others respond more to ocean warming. Warmer Atlantic waters reaching glacier fronts increase submarine melting, removing buttressing ice and allowing upstream ice to accelerate. Still others are controlled primarily by basal conditions, whether the bed is warm enough to produce continuous meltwater, whether the substrate is hard rock or soft sediment that can deform under stress. Understanding which mechanism dominates in which glacier requires detailed knowledge of geometry, bed properties, and thermal state. The new mantle temperature maps contribute directly to this understanding, helping identify which glaciers are most likely to have warm, wet beds, and therefore which ones might be most prone to rapid change. There's also the question of how these thermal patterns might change over time, though on timescales much longer than typical human planning horizons. The heat flow from the mantle isn't entirely constant. It can vary as the mantle slowly convects and as radioactive isotopes gradually decay. The Iceland hotspot itself, though remarkably long-lived, waxes and wanes in intensity over millions of years. As Greenland continues to drift slowly away from Iceland, moving perhaps 2 centimetres per year, accumulating to significant distances over millions of years, the thermal influence of the hotspot will gradually diminish. New volcanic regions may become active elsewhere as the plate motions continue. These changes operate on timescales of millions of years, completely irrelevant to near-term sea level projections, but important for understanding the long-term evolution of Greenland's ice sheet through past glacial-interglacial cycles. During the ice ages of the Pleistocene, when Greenland's ice sheet expanded and contracted multiple times, the thermal structure of the mantle beneath remained roughly constant, providing a steady background against which the ice responded to orbital forcing and atmospheric CO2 changes. The thermal patterns visible in today's models likely influenced how ice accumulated and melted during those past cycles, helping determine which regions were most stable and which were most prone to rapid change. Looking back through ice core records drilled from Greenland's summit, scientists can read climate history directly from the ice itself. Bubbles of ancient air trapped as snow accumulated and compressed into ice provide direct samples of past atmospheres, revealing how CO2 and methane concentrations changed over hundreds of thousands of years. Isotopic ratios in the ice record temperature variations marking glacial and interglacial periods, documenting abrupt climate shifts that occurred in just decades. Dust layers and volcanic ash provide chronological markers, tying the ice record to events recorded in ocean sediments and cave formations elsewhere around the globe. This archive of climate history extends back more than 100,000 years in the longest cores, providing an extraordinary window into Earth's natural climate variability before human influence became dominant. Throughout all these changes, through ice ages when global temperatures were 5 or 6 degrees Celsius colder than today, through warm periods when they were slightly warmer, Greenland retained its ice sheet, though its size and extent varied considerably. The ice core records themselves prove the sheet's persistence, but they also reveal periods of rapid change, times when ice dynamics shifted quickly in response to changing conditions. Understanding what controlled ice sheet behaviour during these past changes helps calibrate models for projecting future changes. If models can successfully reproduce the observed history, matching the timing and magnitude of past ice retreat and advance, matching the rates of change recorded in sea level indicators and ice core evidence, then confidence increases in their projections of future behaviour. But getting the models to match past behaviour requires accurate representation of all the key processes, including basal sliding controlled by geothermal heat. A model that uses the wrong basal heat flux pattern might accidentally get the right answer for the wrong reasons, or might systematically miss important aspects of ice sheet response. The new thermal maps, by providing more realistic boundary conditions, help ensure that models are reproducing past behaviour for the right physical reasons, which in turn increases confidence that their future projections are reliable. The computational challenge of modelling ice sheets continues to push the boundaries of what's possible with current supercomputers. Ice sheets are large. Greenland spans more than 1,500 kilometres from north to south, but they also have fine-scale structure that matters for their behaviour. Crevasses, moulins and ice streams create features ranging from metres to kilometres in size. Bedrock topography includes valleys and ridges at many scales. The ice itself deforms in complex ways, with viscosity that depends on temperature, stress, and crystal structure. Accurate simulation requires resolving these different scales simultaneously, running models with fine spatial resolution but over long time periods, capturing processes that operate over minutes, crevasse formation, days, meltwater drainage, years, glacier acceleration, centuries, ice thickness changes, and millennia, full glacial cycles. The computational grids required can have millions of elements, and tracking ice flow through those grids over simulated centuries requires billions of calculations, even with modern supercomputers running comprehensive ensemble simulations, testing many different scenarios with different assumptions about climate forcing, ice physics and boundary conditions, requires months of continuous computation. The researchers building these models must constantly balance resolution against computational cost, deciding which processes to represent explicitly and which to parameterize with simplified approximations. Basal sliding, for instance, is often parameterized with empirical relationships, rules of thumb that relate sliding velocity to basal stress and water pressure, because explicitly simulating the detailed fluid mechanics of water flowing at the icebed interface would be prohibitively expensive. But these parameterizations need to be based on realistic assumptions about basal conditions, which is where the improved thermal maps become crucial. A parameterization that works well for cold-bedded ice might fail completely for warm-bedded ice. Knowing which regions have which conditions allows modelers to apply appropriate physics in appropriate places. There's an interesting parallel between the patience required in computational modelling and the patience of the processes being modelled. Running an ice sheet simulation for 1,000 simulated years might require weeks of actual computer time, processors churning through calculations day and night, storing terabytes of output data that will later be analysed for trends and patterns. The glacier being simulated moves equally slowly in its own frame of reference, A particle of ice entering the accumulation zone in the interior might take thousands of years to flow to the coast, gradually descending, compressing, warming, deforming, eventually reaching the terminus and calving into the ocean. The computation condenses this vast span of time into manageable duration, but the essence of slowness remains. Ice sheet science requires patience at every level. Patience to collect data over decades, patience to run models over weeks, patience to see how projections evolve as understanding improves, patience to wait for natural experiments like glacier accelerations to play out and provide new information. Perhaps this is part of what makes ice sheet research both frustrating and fascinating for scientists in the field. Unlike laboratory experiments that can be run in hours or days, unlike weather forecasts that verify within days, ice sheet predictions require decades to validate. A projection made today about Greenland's contribution to sea level in 2100 won't be fully testable until researchers currently in graduate school are in retirement. This creates a unique relationship between the science and its timescales. Researchers must work with the understanding that their most important predictions will outlive their careers, that the ultimate test of their models will come long after they've moved on. It requires a kind of intellectual humility, an acceptance that certainty may never arrive, that the best one can do is reduce uncertainties step by step, leaving better tools and better understanding for the next generation to refine further. The communities living around Greenland's coasts already see the changes underway. Fishermen report shifts in fish populations as ocean temperatures change. Hunters notice alterations in sea ice extent and reliability. Towns built on permafrost deal with thawing ground and destabilizing foundations. These local observations, accumulated over lifetimes and generations, provide crucial ground truth that complements the satellite data and model simulations. Indigenous knowledge systems, developed through centuries of close observation and adaptation, contain information about natural variability, about how the environment responds to different conditions, about patterns that might not be captured in the relatively short instrumental record. Integrating this traditional knowledge with modern scientific understanding represents both a challenge and an opportunity. Different ways of knowing, different epistemologies, but ultimately describing the same physical reality. For the people living in places like Ilulissat, where massive Jakobshavn Glacier carves enormous icebergs into Disco Bay, the abstract discussions of mantle temperature and basal sliding become concrete in the changing frequency and size of calving events, in the shifting positions of glacier fronts, in the increasing freshwater flux that affects local marine ecosystems. Tourism has grown around the spectacle of calving glaciers, bringing economic benefits, but also raising questions about how to develop sustainably in a rapidly changing environment. Should communities invest in permanent infrastructure when the landscape itself is transitioning? How do you plan for the future when the baseline keeps shifting? These questions don't have purely scientific answers. They involve values, risk tolerance, economic constraints, and cultural identity. But science can inform them by providing clearer pictures of possible futures, by narrowing the range of uncertainty, by identifying which changes are likely and which are merely possible. The global dimension of these local changes adds another layer of complexity. Meltwater from Greenland doesn't stay in Greenland. It flows into the ocean and redistributes around the globe through currents and tides. Sea level rise is not uniform. Earth's gravitational field, ocean currents, and land motion create regional variations, with some coastlines experiencing more rise than the global average and others less. Freshwater from melting ice affects ocean salinity and density, which influences circulation patterns including the Atlantic meridional overturning circulation, the system of currents that includes the Gulf Stream and helps moderate climate in Europe. Large volumes of fresh water entering the North Atlantic could potentially weaken this circulation, leading to complex climate, effects far from Greenland itself. These teleconnections mean that changes in Greenland's ice sheet have implications that extend well beyond simple sea level contributions, affecting climate patterns, ocean ecosystems, and atmospheric circulation across vast distances. Understanding these connections requires yet another level of modelling complexity. Coupled ice-ocean atmosphere models that simulate all the interacting components simultaneously. The ice sheet influences the ocean by releasing fresh water and icebergs. The ocean influences the ice sheet by carrying heat to glacier fronts. The atmosphere influences both ice and ocean through temperature, precipitation, and wind. The ice and ocean influence the atmosphere through albedo effects, humidity changes, and heat exchange. These feedbacks can amplify or dampen changes, create tipping points, lead to non-linear responses where small pushes produce large outcomes. Disentangling cause and effect in such a coupled system challenges even the most sophisticated models, and observations that could validate the models remain sparse. Progress comes through careful comparison of models with observations, through process studies that isolate particular mechanisms, through natural experiments like past climate changes that test whether models can reproduce what actually happened. The mantle temperature maps fit into this larger effort as one piece of the foundation. Better boundary conditions that allow more accurate ice sheet models, which in turn can be better coupled with ocean and atmosphere models, gradually building toward comprehensive Earth system models that capture the full complexity of interactions. Each improvement is incremental. Each new data set refines understanding slightly. Each model advance narrows uncertainties a bit more. There are no eureka moments, no sudden breakthroughs that solve everything at once. Instead, there's the steady accumulation of knowledge, the patient building of infrastructure, observational networks, computational capabilities, theoretical frameworks, collaborative relationships that enable science to slowly converge on more reliable representations of reality. Night deepens over the ice sheet, and far above, the aurora begins its dance, sheets of green and occasionally red light rippling across the sky, produced by solar particles interacting with Earth's magnetic field and atmosphere. This light show, beautiful and ethereal, represents yet another connection between processes at vastly different scales. Nuclear fusion in the Sun's core producing the energy that accelerates particles, the Earth's liquid iron outer core generating the magnetic field that channels those particles toward the poles, atmospheric atoms emitting photons as they're excited and return to ground states. The aurora has been visible from Greenland for as long as Greenland has existed, long before ice covered it, witnessed by no eyes for most of that time, a physical phenomenon, proceeding regardless of observation. The ice below, the mantle beneath that, the processes that shape them all. These two operated for millions of years without witness, without measurement, without understanding. Only in the last few centuries, and especially in the last few decades, have humans developed the tools to observe and comprehend these systems, to measure their behavior, to project their futures. This recent acquisition of observational and predictive capability comes at a crucial moment, as human activities drive changes to Earth's climate more rapid than anything in the geological record since the asteroid impact that ended the Cretaceous period. The atmosphere's CO2 concentration has risen from pre-industrial values around 280 parts per million to over 420 parts per million today, a change that took only about 2 centuries, a geological instant. Earth's climate is responding, with global average temperatures already more than 1 degree Celsius above pre-industrial baselines and continuing to rise. Ice sheets, glaciers, sea level, ecosystems, all are adjusting to this new forcing, and the adjustments are only beginning. The full response will unfold over centuries and millennia, long after current greenhouse gas emissions have ceased, because the climate system has immense inertia. Ice sheets are particularly slow to respond, with equilibration timescales of thousands of years, meaning that even if atmospheric CO2 were stabilized tomorrow, ice would continue adjusting for millennia as it slowly catches up with the new climate state. The value of research like the new mantle thermal mapping lies partly in improving near-term projections for planning purposes, but also in understanding the longer-term committed changes already in motion. Humanity has already altered the planetary energy balance enough to ensure significant future sea level rise even with aggressive emissions reductions. The questions are how much, how fast, and over what timescales. Better ice sheet models, informed by better knowledge of basal conditions, help answer these questions, providing essential information for adaptation planning. Coastal communities need to know not just that seas will rise, but how quickly and how much, so they can make informed choices about whether to protect, accommodate, or retreat. Engineers designing infrastructure that must last 50 or 100 years need projections of local sea level over those timescales. Insurance companies assessing flood risk need probabilistic forecasts. All of these stakeholders depend on the slow, careful work of researchers, gradually improving understanding of ice dynamics, basal processes, climate forcing, and how these factors combine to determine future ice sheet behavior. The ice itself, oblivious to human concerns, continues its slow journey, molecule by molecule, crystal by crystal, flowing downhill under its own weight, shaped by forces both visible and hidden. Above, the climate warms. Below, the mantle glows. Between these two reservoirs of heat, the ice exists in a delicate balance, maintained by the cold of polar winters and the shield of altitude, but perpetually under siege from warmth above and warmth below. For millennia, that balance held relatively steady, with the ice advancing in cold periods and retreating in warm ones, but remaining a permanent feature of the Greenland landscape. Now the balance shifts, tipping toward retreat, accelerating as feedbacks amplify the forcing. The bright white surface that once reflected sunlight back to space darkens as melt exposes bare ice and dust. Meltwater carving channels to the bed increases sliding in summer months. Ocean waters warming by fractions of a degree reach deeper into fjords, melting glacier fronts from below. Each of these effects is small individually, but together they compound, pushing the system in one direction. The next story is about to begin. Please relax and enjoy. The lava flows at night, a river of molten orange sliding down the dark Hawaiian slope with the patience of honey. Where it meets the ocean, steam rises in white plumes that glow against the starlit sky, and the rock hardens from brilliant orange to deep crimson to black in the space of seconds. Each pulse of magma emerges from the earth like a breath, slow and steady, as if the planet itself is exhaling something it has held deep inside for longer than we can imagine. Lie down now. Let your breathing match the rhythm of this flow, slow, unhurried, constant. Tonight's story is about a connection so hidden and so gradual that no human will ever witness it directly, yet it shapes the ground beneath every step we take. It's about how the metallic heart of our planet, thousands of kilometers below, is not entirely sealed away from the rocky world above. Over billions of years, material from Earth's iron core has been leaking upward through the mantle, carried in slow currents of hot rock, eventually arriving at the surface in places like Hawaii as volcanic stone. This leaking is not sudden or violent. It is gentle, exceedingly slow, part of a deep circulation that keeps Earth alive and ever-changing. Pull back now from the lava, away from the island, up through the atmosphere until Earth hangs in space before you, a sphere of blue oceans and white clouds, beautiful and serene. But imagine it sliced open like a layered cake, revealing what lies within. At the very outside is the crust, thin and brittle as eggshell, the only layer we ever touch. Below that stretches the mantle, a vast shell of rock that is solid yet flows like putty over millions of years, making up most of Earth's volume. And deeper still lies the core, an outer layer of liquid iron and nickel, churning and convecting, and at the very centre a solid sphere of metal under such immense pressure it cannot melt despite temperatures rivaling the surface of the sun. Heat escapes from this core and from the deep mantle over time, and that escaping heat drives slow convection. Imagine enormous currents of rock creeping through the mantle at speeds comparable to the growth of your fingernails. Hot rock rises, cools near the surface, then sinks again in a cycle that takes tens of millions of years to complete. The mantle is not quiet or static. It is a slow river system on a planetary scale, transporting heat and material in patterns that shape continents and ocean basins. Descend now into the mantle itself. Picture it not as empty darkness, but as a dimly glowing realm of dense rock under unimaginable pressure, lit from within by its own heat. In places, hotter rock gathers into columns and begins to rise, ascending through the surrounding mantle like a plume of warm air rising through cooler atmosphere. These are called mantle plumes, and they can persist for millions of years, feeding volcanic hotspots far from the edges of tectonic plates. Hawaii is one such place, a chain of volcanic islands built atop a plume that has been active for perhaps 40 million years or more. The motion here is almost imperceptibly slow. If you could watch the mantle in fast forward, you would see broad glowing streams rising and cooler currents sinking, everything moving with the grace of syrup poured through honey. A single loop of this convection, from deep mantle to near surface and back again, might take longer than the entire existence of humanity as a species. Think of it as the planet's deep, slow breathing. Hot rock rises like an inhale, cooler rock sinks like an exhale, over and over, in a rhythm measured not in seconds but in geological ages, sink deeper now, down through the lower mantle, toward the very base of this rocky shell. At the boundary between mantle and core, about 2,900 kilometers below your feet, seismic waves reveal something strange. Two continent-sized regions where the rock behaves differently. These are called large low shear velocity provinces, or LLSVPs, and they sit like vast submerged mountains beneath Africa and the Pacific Ocean. Seismic waves slow down as they pass through these regions, suggesting the rock here is denser, hotter, or chemically distinct from the surrounding mantle. Scattered around their edges are smaller ultra-dense patches called ultra-low velocity zones, or ULVZs, where seismic waves slow even more dramatically. These structures are enormous. Each LLSVP is wider than a continent and hundreds of kilometers tall. They are perched right at the interface between the rocky mantle and the liquid metal core, like enormous basins or mountains at the floor of a planetary ocean. Scientists think they may be leftovers from Earth's earliest days, when the entire surface was covered in a magma ocean and the interior was still sorting itself into layers. Some of that molten rock, perhaps mixed with material diffusing from the newborn core, may have sunk to the base of the mantle and solidified there, creating these strange provinces that persist today. The Pacific LLSVP sits directly beneath the ocean where Hawaii's volcanic chain grows, and some of the ULVZs nest near its edges. The hotspot above may be anchored to these deep structures, drawing its heat and material from this hidden reservoir far below. Return briefly to the surface. Imagine a geologist's hand holding a piece of dark volcanic rock from Hawaii, its surface rough and glassy, tiny crystals catching the light. In laboratories, scientists have analysed rocks like this, searching for clues about where the magma came from. In recent years, they found something surprising: subtle anomalies in the isotopes of ruthenium, a precious metal that should mostly reside in Earth's core. The chemical signature of these Hawaiian rocks doesn't quite match the average mantle. Instead, it hints that some of the material has interacted with or originated near the core itself, thousands of kilometers below. Isotopes are variants of the same element, identical in chemistry but slightly different in mass. Over time, natural processes fractionate them in characteristic ways, leaving a fingerprint that reveals an element's history. By measuring isotope ratios with extreme precision, geochemists can infer where magma's ingredients came from. The ruthenium anomaly in Hawaiian basalt suggests the lava carries with it a faint trace of the core, as if something from the metallic deep has made its way upward through the mantle and surfaced in these volcanic rocks. The connection is tenuous, indirect, but it's there, a whisper from the planet's hidden heart. Follow that whisper downward now. Imagine riding a stylized mantle plume from the Hawaiian hotspot into the depths, past the magma chamber beneath the volcano, through the brittle upper mantle where earthquakes occur, into the lower mantle where pressure turns familiar minerals into strange dense forms. The plume appears as a broad column of slightly warmer rock, glowing faintly against the darker mantle around it, rising with the patience of continents drifting. This plume likely originates near the core mantle boundary, perhaps where a ULVZ or the edge of an LLSVP focuses heat and buoyancy into an upward current. The descent is like a slow elevator ride through layers of colour and texture. Crystals deform under mounting pressure, minerals rearrange their atoms into tighter structures, temperature climbs, and the sense of weight becomes overwhelming. Not violent, but immense, the weight of an entire planet pressing inward. The plume is not a violent jet of molten rock shooting upward. It is a patient, persistent stream of slightly hotter material making its way through the mantle over tens of millions of years, millimetre by millimetre, slower than the slowest glacier, yet unstoppable in its buoyancy. At last you arrive at the core mantle boundary, a thin, rough interface that separates two fundamentally different worlds. Above lies the mantle, solid rock that flows. Below lies the outer core, liquid metal in constant motion. Imagine it as a ragged coastline in total darkness, with ridges of dense LLSVP material rising like undersea mountains, and low-lying ULVZ ponds where partially molten rock has pooled. Just beneath this boundary, the outer core churns, a swirling ocean of liquid iron alloy, its convection generating the magnetic field that shields Earth's surface from solar radiation. Here, conditions are extreme but steady. Temperatures reach several thousand degrees Celsius, hot enough to vaporize any substance at the surface, yet the rock remains solid under pressures millions of times greater than atmospheric. The metal remains liquid, its atoms jostling and flowing in great convective rolls that twist magnetic field lines into complex patterns. This boundary is not a perfect seal. Over immense spans of time, light elements and trace metals can diffuse or leak from the core into the overlying mantle, subtly altering its chemistry and density. Picture it now in abstract. Coloured streams and glowing dots representing atoms crossing the core mantle boundary. The core and mantle are not perfectly isolated from each other. Models and geochemical evidence suggest a slow exchange of elements, silicon, oxygen, magnesium and trace metals, between the liquid iron of the core and the lowermost mantle rock. In Earth's youth, when a global magma ocean covered the surface and the interior was still molten, core material likely mixed into the base of the solidifying mantle. This early mixing prevented the planet from separating into rigid chemical layers and left a legacy of heterogeneity in the deep mantle that persists today. The leaking continues, though it is not really a leak in any dramatic sense. It is more like a drip, unimaginably slow but persistent over billions of years. Tiny contributions accumulate into noticeable differences in the chemistry of mantle regions and hotspot lavas. This deep mixing may be part of why Earth's mantle remains so active, and why the planet's evolution took a different path than more geologically stagnant worlds. Without this gradual exchange, the mantle might have stratified into chemically distinct layers that resist mixing, choking off the convection that drives plate tectonics and volcanic activity. Trace the path now from boundary to surface. Core-derived elements enter the lowermost mantle, perhaps diffusing into the dense rock of an LLSVP, or mixing into the partially molten material of a ULVZ. Over time, some of this altered rock becomes entrained in a rising mantle plume, carried upward by buoyancy. As the plume ascends and pressure decreases, parts of the rock begin to melt. These melts are less dense than the surrounding solid rock, so they separate and migrate upward, pooling in reservoirs in the upper mantle. Eventually they feed magma chambers beneath volcanoes and erupt as basaltic lava at hotspots like Hawai or other ocean islands. Only a tiny fraction of the plume's deep chemical signature appears in each eruption, which is why sensitive isotope measurements are needed to detect it. But that fraction is enough to tell us that the material in these surface rocks has travelled from the core mantle boundary, a journey of nearly 3,000 kilometres upward through the planet's interior. The process is a kind of planetary circulation system. Old oceanic crust sinks at subduction zones, descending into the mantle where it is heated and transformed. Some of it may eventually reach the core mantle boundary, interact with the deep structures there, then resurface very slowly through plumes over millions of years. What sinks can eventually rise. What rises cools, hardens, and may one day sink again. The cycle continues, endlessly patient. Zoom out now to see the big picture. This deep recycling and mixing is not just an obscure detail of planetary science. It influences Earth's habitability in profound ways. The style of volcanism, the growth of continents, the release of gases to the atmosphere, the strength and stability of the magnetic field, all are shaped by how heat and material circulate through the deep interior. The peculiar structures at the base of the mantle, shaped in part by core mantle interaction, may have helped keep Earth's interior dynamic enough to support long-term plate tectonics and a stable climate, both of which are essential for life. This is not about dramatic events or catastrophic upheavals. It is about slow balance. Too little internal activity, and a planet becomes geologically dead, its surface cold and unchanging, unable to recycle nutrients or regulate climate. Too much activity, and the surface might be too hostile for complex life to gain a foothold. Earth has found a middle path, a long steady rhythm where deep processes and surface environments gently co-evolve. The hidden circulation at the core mantle boundary is part of that rhythm, a quiet engine that has been running for billions of years and will continue long after we're gone. Consider the timescales involved. Imagine a time-lapse of Earth over billions of years, continents drifting across the surface like rafts on a slow current, ocean basins opening and closing, volcanic chains appearing and fading as plumes wax and wane. Core mantle exchange and plume cycles operate over tens to hundreds of millions of years. A single loop from core mantle boundary to surface and back might outlast entire species, whole mountain ranges rising and eroding away in the time it takes for one packet of deep material to complete its journey. Contrast this with human timescales, the decades of a lifetime, the centuries of recorded history. We move quickly through our days, measuring time in heartbeats and breaths, worrying about deadlines and appointments. The planet's deep machine is not hurried. It moves at a pace that makes our daily concerns seem very small and very brief, and there is something oddly comforting in that. While we focus on moments, Earth's hidden heart moves on a schedule closer to eternity, unconcerned with anything but its own slow turning. Return now to the surface, to where we began, a Hawaiian lava flow at night, viewed from a little farther away. The molten rock glows softly in the darkness, a ribbon of orange light against black stone, clouds of steam rising where it meets the sea. Above, stars appear between drifting volcanic clouds, brilliant and cold against the night. Below, unseen, the plume continues to feed magma from deep within the mantle, carrying with it faint chemical echoes of the core mantle boundary. Somewhere far beneath your feet, at a frontier you will never see, the planet's metallic heart and rocky mantle are still exchanging material in tiny amounts. This exchange, invisible and infinitesimally slow, keeps Earth's interior lively and its surface ever-changing. It is a hidden heartbeat, a warm, steady engine pulsing, quietly through geological ages, content to keep turning while continents drift, oceans rise and fall, and species come and go. Picture that heartbeat now as your own breathing slows. Deep below, at the core mantle boundary, iron atoms diffuse into rock. Somewhere in the lower mantle, a plume begins its long ascent, warmer than its surroundings by just a few degrees, but buoyant enough to rise. Over millions of years, it will carry deep material upward, eventually reaching the surface as lava in some distant volcanic field. The rocks that form will carry with them a faint signature of the core, a chemical whisper from the planet's centre, testifying to a connection that spans nearly the entire radius of the Earth. This is the story of the leaking core. Not a catastrophe or a crisis, but a gentle, persistent exchange that has been happening since the planet was young and will continue for billions of years to come. It is the story of how Earth's deepest interior and its surface are not separate but connected through slow circulation. How what seems solid and unchanging is actually moving and mixing on timescales beyond imagination, and how the ground beneath us is part of a vast living system that extends from the centre of the planet to the edge of space. Let that image settle in your mind. A warm, patient engine turning far below, moving rock and metal in a rhythm older than mountains, slower than erosion, steady as the stars. The lava flows at night, and somewhere deep in the earth, the core leaks its secrets upward, one atom at a time, while we sleep and dream, and the planet continues its ancient, unhurried work. And yet there is more to understand about this quiet exchange, more layers to the story that unfold when we linger in the deep places and let the scale of planetary time wash over us. The core mantle boundary is not merely a surface where two layers meet. It is a dynamic region, a zone of interaction where the properties of matter are pushed to their limits and where the physics of our everyday world no longer applies in familiar ways. Here, the distinction between solid and liquid becomes less clear, and the very concept of a boundary begins to blur into something more gradual, more nuanced. Think about the outer core for a moment. That vast ocean of liquid metal swirling in the darkness. It is not still. Convection currents driven by heat escaping from the solid inner core create flows that can reach speeds of kilometres per year. Glacially slow by the standards of water or air, but remarkably fast for the deep interior of a planet. These flows organise themselves into complex patterns, rising columns of hotter metal, sinking sheets of cooler metal, and vast rotating vortices that stretch from pole to pole. As the liquid iron moves, it carries with it magnetic field lines, stretching and twisting them in ways that sustain Earth's magnetic field through a process called the geodynamo. This magnetic field is not a minor detail. It extends far beyond the planet's surface, creating a protective bubble called the magnetosphere that deflects most of the charged particles streaming from the sun. Without it, Earth's atmosphere would be slowly stripped away by the solar wind, as happened to Mars billions of years ago. The magnetic field, generated by motion in the core, is part of what makes the surface habitable, and that motion, in turn, depends on heat flow across the core mantle boundary, which is influenced by the composition and structure of the lowermost mantle, the very region where core material may be leaking upward. The connection runs deeper still. The outer core is not pure iron. It contains lighter elements, perhaps sulfur, silicon, oxygen, carbon or hydrogen, that lower its density and melting point. Some of these light elements may have been incorporated when Earth formed, but others may continue to enter the core from the mantle, or leave the core for the mantle, through slow chemical reactions at the boundary. When iron in the outer core crystallizes onto the solid inner core, the light elements are excluded, making the surrounding liquid slightly less dense and causing it to rise. This process releases gravitational energy that helps drive the convection, adding to the thermal buoyancy from heat flow. In this way, the leaking of material across the core mantle boundary is intimately tied to the generation of Earth's magnetic field. A change in the rate of exchange, or in the composition of what is exchanged, could alter the vigour of core convection and thus the strength of the magnetic field. Over Earth's history, the magnetic field has varied in intensity and has even reversed its polarity many times, with north and south magnetic poles switching places. These reversals may be influenced by changes in the deep mantle, by the arrival or departure of subducted slabs at the core mantle boundary, or by shifts in the geometry of the LLSVPs. The deep interior and the magnetic shield that protects life at the surface are coupled in ways we're only beginning to understand. Consider also the heat itself, the energy that drives all of this motion. Earth's interior is hot for two main reasons. It retains primordial heat from the planet's violent formation, when countless collisions of smaller bodies released enormous amounts of energy, and it generates new heat through the radioactive decay of elements like uranium, thorium and potassium scattered through the mantle and crust. This heat must escape, and it does so through a combination of conduction, atoms jostling their neighbours, and convection, the bulk motion of hot material rising and cool material sinking. In the mantle, convection dominates. The rock is solid on human timescales but flows over millions of years, transporting heat far more efficiently than conduction alone could. At the core mantle boundary, heat flows from the hot core into the cooler base of the mantle. The rate of this heat flow determines how vigorously the core convects, how fast the inner core grows, and how much power is available to sustain the magnetic field. But the rate of heat flow is not uniform across the boundary. The LLSVPs, with their unusual composition and thermal properties, may act as insulators, reducing heat flow in some regions while allowing it to be more vigorous in others. This patchwork of heat flow may organise the pattern of mantle plumes, concentrating them around the edges of the LLSVPs, which is indeed where many hotspots like Hawaii are found. The presence of the LLSVPs and ULVZs also raises questions about Earth's early history. When the planet was young, only a few 100 million years after its formation, a Mars-sized body called Theia is thought to have collided with the proto-Earth in a cataclysmic impact. This giant impact melted much of both bodies, ejecting a huge amount of material into orbit that eventually coalesced into the Moon, and leaving Earth with a deep magma ocean. For millions of years, the surface may have been entirely molten, glowing red-hot under a thick atmosphere of vaporized rock. As this magma ocean slowly cooled and solidified from the top down, denser minerals crystallized and sank, while lighter minerals formed a crust that floated. But the very bottom of the mantle, in contact with the core, may have remained partially molten for much longer. Some researchers believe the LLSVPs could be remnants of this ancient magma ocean, dense piles of crystallized rock that sank to the base of the mantle and have persisted for billions of years. If so, they are among the oldest structures in the planet, silent witnesses to an era when Earth's surface was a hellish landscape of molten rock under a sky filled with vapour. Others propose that the LLSVPs could be accumulations of subducted oceanic crust, the remains of ancient seafloor that has been pushed down into the mantle at convergent plate boundaries and has settled at the core mantle boundary because it is denser than the surrounding mantle. Over billions of years, enough of this material could have accumulated to form the enormous provinces we see today. Yet another possibility is that the LLSVPs are enriched in iron or other dense elements that leaked out of the core early in Earth's history, when the core mantle boundary was hotter and more chemically active than it is now. Each of these hypotheses paints a different picture of Earth's evolution, yet all agree on one point. The deep mantle is not a simple uniform layer, but a complex archive of the planet's history, storing information about ancient processes in its structure and composition. The ULVZs, those smaller and even denser patches at the base of the mantle, add another layer of mystery. Some may be partially molten, with temperatures just above the melting point of mantle rock at those extreme pressures. Others may be rich in iron, having accumulated metal that leaked from the core or that was delivered by subducted material enriched in iron oxides. The existence of these structures challenges our understanding of how planets work. On a simpler world, one without plate tectonics or vigorous mantle convection, the interior might stratify into neat chemical layers and remain that way for billions of years. But Earth's interior is stirred by convection, mixed by plumes and slabs, and enriched or depleted by exchange with the core. The result is a mantle that is heterogeneous on all scales, from the tiny variations in mineral composition within a single rock sample to the continent-sized LLSVPs at the base of the mantle. This heterogeneity is not chaos. It is a kind of order born from complexity, a record of processes operating over vastly different timescales and length scales. A packet of rock in the deep mantle may carry with it a memory of where it came from, whether it originated as oceanic crust formed at a mid-ocean ridge, whether it spent time near the core mantle boundary absorbing heat and trace elements, whether it was melted and resolidified in a plume. Geochemists, by analysing the isotopes in volcanic rocks, can begin to read this memory, tracing the pathways that material has taken through the mantle over hundreds of millions of years. The isotopes of ruthenium found in Hawaiian lavas are one such clue. Ruthenium is a siderophile element, meaning it has a strong affinity for iron and preferentially partitions into metal rather than rock. During Earth formation, as the core separated from the mantle, most of the ruthenium should have sunk into the core along with the iron. The mantle should be depleted in ruthenium, and what little remains should have a particular isotopic composition. But some Hawaiian lavas show isotopic ratios that suggest they contain ruthenium that behave differently, that came from a source with a different history, possibly one that interacted with the core. The signal is subtle, a shift of just a few parts per million in the ratio of different ruthenium isotopes, but it is measurable and consistent across multiple samples. It suggests that the Hawaiian plume is sampling a region of the mantle that has been enriched in core-derived material, perhaps through the slow leaking of elements across the core mantle boundary over billions of years. Other isotopic systems, tungsten, osmium, helium, tell similar stories, each adding a piece to the puzzle of how the deep mantle is connected to the core and how that connection manifests in surface volcanism. Helium is particularly interesting. The mantle contains two isotopes of helium, helium-3 and helium-4. Helium-4 is produced by radioactive decay of uranium and thorium, so it accumulates over time in the mantle and crust. Helium-3, on the other hand, is primordial. It was incorporated into Earth when the planet formed and has been slowly leaking out ever since. Volcanic gases from hotspots like Hawaii and Iceland contain higher ratios of helium-3 to helium-4 than gases from mid-ocean ridges, suggesting that hotspot plumes are tapping into deep, ancient reservoirs of mantle that have retained their primordial helium. This primordial helium must have been stored somewhere in the deep mantle, isolated from the vigorous mixing of the upper mantle for billions of years. The LLSVPs are candidates for such storage. If they are indeed ancient structures, they could have preserved pockets of primordial mantle composition even as the rest of the mantle was stirred and homogenized by convection. When a plume rises from the edge of an LSVP, it brings with it a sample of this ancient material, releasing helium-3 that has not seen the surface since the planet was young. The same plume also carries heat, of course, and that heat is ultimately what drives the volcanism at the surface. But the heat itself has a history. Some of it is primordial, left over from Earth's formation, and some is generated by radioactive decay. The heat from the core adds to this, flowing outward through the mantle and eventually radiating into space. The rate at which Earth is losing heat has been debated for centuries, ever since Lord Kelvin attempted to calculate the age of the Earth by modelling how long it would take for a molten sphere to cool. Kelvin's estimate, based on conduction alone, was far too short, only tens of millions of years, because he did not account for convection or radioactive heating. Modern estimates, based on measurements of heat flow at the surface and models of mantle convection, suggest Earth is losing about 47 terawatts of heat, roughly the energy of 10,000 large power plants running continuously. Of this heat, perhaps 5 to 15 terawatts comes from the core, with the rest generated in the mantle and crust by radioactive decay. The core, despite being enormously hot, is gradually cooling as it loses heat to the mantle. This cooling causes the inner core to grow as iron crystallizes from the liquid outer core, releasing latent heat and light elements that drive further convection. The process is self-sustaining as long as there is heat to lose, and models suggest it will continue for billions of years, until the core has cooled to the point where convection ceases and the magnetic field dies. But the rate of core cooling depends on the thermal conductivity of the lowermost mantle, and this is where the LLSVPs and ULVs come back into the story. If these structures act as thermal blankets, insulating the core, they slow the rate of heat loss and prolong the life of the geodynamo. If they are more conductive, or if they are eroded away by mantle convection, the core cools faster. The future habitability of Earth, millions or billions of years from now, may depend in part on the stability and properties of these deep structures, on whether they persist or dissolve as the mantle continues to churn. There is also the question of symmetry. The two, LSVPs under Africa and the Pacific, are not identical. The African LSVP is taller and more dome-shaped, while the Pacific LSVP is broader and flatter. They differ in their seismic properties, suggesting differences in composition or temperature. Why should there be two rather than one or many? And why are they located where they are, under particular regions of the surface? These questions touch on the deepest mysteries of mantle dynamics. One possibility is that the locations of the LLSVPs are controlled by the pattern of subduction at the surface. Slabs of oceanic crust sink into the mantle at subduction zones, and over time these slabs may accumulate in certain regions of the deep mantle, building up piles of dense material. Computer models show that subduction patterns can organize themselves into long-lived configurations, with slabs preferentially sinking in some regions and avoiding others. The regions where slabs accumulate could become the LLSVPs, while the regions they avoid could become pathways for plumes to rise. This would create a kind of planetary scale circulation pattern. Slabs sink at convergent boundaries, descend through the mantle and pile up at the core mantle boundary in preferred locations. The piles act as anchors, around which the rest of the mantle flows. Plumes rise from the edges or tops of the piles, fed by heat from the core and carrying with them material that has been enriched by interaction with the core or with the subducted slabs. The plumes reach the surface at hotspots, feeding volcanoes that create island chains and flood basalts. Eventually, the volcanic rocks at these hotspots are carried away by plate tectonics, subducted, and sent back down into the mantle, completing the cycle. This cycle operates over hundreds of millions of years, but it is not a closed loop. Material is constantly exchanged between different reservoirs. The crust, the depleted upper mantle, the enriched deep mantle, transition zone, the LLSVPs, and the core. Some material may circulate rapidly, returning to the surface within a few 100 million years. Other material may become trapped in the deep mantle, isolated from the surface for billions of years, and a small fraction may exchange with the core, carrying trace elements back and forth across the core mantle boundary over the entire age of the Earth. The result is a mantle that is neither well mixed nor perfectly layered, but something in between, a marble cake of compositions, temperatures and histories, stirred but not homogenized, retaining memory of the past while constantly evolving. This is the mantle that feeds the volcanoes we see at the surface, and it is why volcanic rocks are so diverse in their chemistry and isotopic composition. Each volcano is sampling a different part of this heterogeneous mantle, and by studying the rocks carefully, we can begin to map the mantle's internal structure and trace the pathways of material circulation. The implications extend beyond geology. The gases released by volcanoes, water vapor, carbon dioxide, sulfur dioxide, and many others, have shaped Earth's atmosphere and climate over billions of years. The early atmosphere was likely dominated by gases outgassed from the interior, with oxygen only becoming abundant after photosynthetic life evolved and began producing it as a waste product. Even today, volcanic outgassing plays a role in the carbon cycle, releasing carbon dioxide that would otherwise be locked away in subducted carbonate rocks. Over millions of years, the balance between volcanic outgassing and the removal of carbon dioxide by weathering and subduction helps regulate Earth's climate, keeping it within a range that allows liquid water to exist at the surface. This regulation is not perfect. Earth has experienced ice ages and hothouse periods, but it has been remarkably stable compared to other planets. Venus, with a thick carbon dioxide atmosphere and surface temperatures hot enough to melt lead, may have lost its oceans early in its history due to a runaway greenhouse effect. Mars, with a thin atmosphere and a cold, dry surface, may have lost much of its atmosphere to space after its magnetic field shut down. Earth, by contrast, has maintained liquid water at its surface for at least 3.5 billion years, perhaps longer, allowing life to originate and evolve into the complex biosphere we see today. The deep circulation of the mantle, the exchange of material with the core, the generation of the magnetic field, the release of gases through volcanism, all of these processes are interconnected, forming a planetary system that has sustained habitability over immense spans of time. And at the heart of this system, literally, is the core mantle boundary, where heat and material flow between the metallic heart of the planet and the rocky shell that surrounds it. Imagine returning once more to that boundary, to the ragged interface in the deep darkness. Iron atoms vibrating with thermal energy occasionally break free from the liquid metal of the outer core and diffuse into the overlying rock. Silicon or oxygen atoms from the mantle dissolve into the liquid core. The exchange is reciprocal, driven by differences in chemical potential and temperature, governed by the laws of thermodynamics operating at conditions we can only approximate in laboratories. Over billions of years, the cumulative effect of this exchange is to blur the distinction between core and mantle, to create a transition zone enriched in both rock-forming and metal-forming elements, a hybrid region that belongs fully to neither realm. This transition zone may be where the ULVs reside, patches of rock that are unusually rich in iron or partially molten due to the presence of core-derived elements that lower the melting point. Seismic waves struggle to pass through these zones, slowing down and scattering in ways that reveal their presence but leave their detailed structure uncertain. They are thin, perhaps only a few tens of kilometers thick, but they are dense enough to affect the dynamics of the core mantle boundary, perhaps influencing where plumes nucleate or where heat flow is concentrated. Plumes rising from the boundary may entrain some of this material, carrying it upward as they ascend through the mantle. The journey is long and the conditions change dramatically along the way. Pressure drops by more than 1 million atmospheres, temperature decreases by over 1,000 degrees, and minerals transform from one crystal structure to another as they pass through different stability fields. The plume material partially melts as it rises, with the melt fraction increasing as pressure drops and volatile elements like water or carbon dioxide, if present, lower the melting temperature further. By the time the plume reaches the base of the lithosphere, the rigid outer shell of the Earth, it has been transformed. What began as solid rock at the core mantle boundary is now a mixture of solid crystals and liquid melt, with the melt enriched in elements that preferentially enter the liquid phase. This melt is buoyant, less dense than the surrounding solid rock, so it segregates and rises, percolating through the matrix of crystals like water rising through a sponge. It collects in magma chambers beneath volcanoes, where it may reside for thousands or millions of years, slowly crystallizing and evolving in composition before finally erupting at the surface. The eruption itself is a release, a sudden opening of a pathway from the deep interior to the surface. Magma rises through fractures in the crust, driven by the pressure of dissolved gases expanding as pressure decreases. At the surface, lava pours out, glowing and incandescent, cooling in the air or ocean water. Gases bubble out, forming clouds of steam and volcanic fumes, and the rock, once it solidifies, becomes part of the crust, a new addition to the skin of the planet, but carrying within it a chemical memory of its long journey from the deep mantle, perhaps from the very edge of the core. This is how the core's secrets reach the surface, not directly, but through a long chain of processes, each transforming the material a little more, each adding its own signature. The geochemist, examining a hand sample of basalt, is reading a message written in isotopes and trace elements, a message that has travelled 3,000 kilometres and taken millions of years to arrive. The message is faint and fragmented, but it is there, testifying to the connectedness of the planet, to the way that the deepest interior and the thinnest surface layer are linked by the slow circulation of the mantle. And so the cycle continues, as it has for over 4 billion years and as it will for billions more. Slabs sink, plumes rise, the core cools and the mantle flows. Material moves between reservoirs, mixing and separating, enriched and depleted, carrying heat and elements and isotopes from one region to another. The surface is constantly renewed, old crust recycled into the interior and new crust generated by melting. The magnetic field flickers and reverses but persists, shielding the surface from the solar wind. The climate fluctuates but remains within bounds that allow liquid water and life. None of this happens quickly. A single human lifetime is far too short to observe the motion of the mantle or the drift of continents. But our species has existed long enough and developed the tools to see far enough that we can begin to perceive these slow processes, to measure their rates and trace their effects. We can send seismic waves through the planet and map its internal structure. We can measure isotopes with enough precision to detect the fingerprint of the core in a volcanic rock. We can build computer models of mantle convection and test them against observations. And piece by piece, we are assembling a picture of how the planet works, how its many parts interact, and how the system as a whole has sustained itself over deep time. The story of the leaking core is part of that larger picture. It tells us that the boundaries we draw on diagrams between crust and mantle, between mantle and core, are not absolute barriers but permeable interfaces across which material and energy flow. It tells us that the planet is not a static structure but a dynamic system, constantly evolving, its past inscribed in its present structure, its future shaped by processes that began billions of years ago and will continue long after our time. There is a deep comfort in understanding this, in seeing ourselves as brief witnesses to a system so much older and larger than we are. The lava flows in Hawaii tonight, as it has flowed for millions of years and as it will continue to flow for millions more. The plume beneath the islands rises, fed by heat from the core mantle boundary, bringing with it traces of the planet's metallic heart. And deep below, in the total darkness, iron atoms continue their slow diffusion into rock, patient and persistent, contributing their tiny part to the grand circulation that keeps the planet alive. Let your mind rest on that image, the warm darkness of the deep interior, the slow upwelling of heat, the patient exchange of atoms across a boundary far below, and the eventual emergence of that deep material at the surface as glowing lava under the stars. It is all connected, all part of one vast planetary system, operating on timescales that dwarf our own, but proceeding with a regularity and persistence that is, in its way, deeply reassuring. The Earth abides, its hidden heart beating quietly through the ages, and we are here, for this brief moment, to marvel at its workings and to tell its story.